Let us now discuss a new paradigm of designing multiprocessor systems. We call this multithreading. So the approach in multithreading is slightly different. It does not use as many resources as a traditional multi-core processor, and it is still regarded as very efficient. And multithreading has also been there since at least the last 10 or 15 years, and it has been more or less adopted by large sections of the processor industry. So, recall that we have heard the word thread before. So, we heard it in the context of a running instance of a program. Sorry. Uh, we differentiated between two terms at that point. One was a process, and the other was a thread. So, a process again was defined as a running instance of a program. However, two processes in general do not share the address space, but two threads actually can share the address space. It is possible for two threads in principle to share the address space, large parts of the address space. So multithreading is basically a design paradigm that proposes to run multiple threads on the same pipeline. So we have designed a pipeline in a previous chapter. So a pipeline of a modern processor is typically more complicated, and our pipeline was able to process only one instruction at a time. But modern processors can, process 3, 4, 5, 6 instructions at at a time inside a single stage. So they are far more complicated, but the basic idea still remains the same. So in a multi-threaded system, typically what happens is that a single pipeline can execute instructions from multiple threads at once. So inside the pipeline, you will have instructions not just from one thread, but you will have them from multiple threads. For example, if there are threads T1 to T4, you'll have some instructions of T1, some of T2, some of T3, and some of T4. So the pipeline will know how to execute instructions for all of these four threads. So this will, in a sense, increase our throughput, because sometimes it does happen. Typically, when we are accessing memory, that assume that in for thread T1, it misses in the L2 cache, so the request has to go all the way down to main memory, right? So all the way down to main memory, the request needs to go. So for 200 or 300 cycles, T1 will not be able to make any progress. During this time, instead of idling, we can get instructions from other threads and execute them. So this will increase and improve our net throughput. So with this insight in mind, let's look at three kinds of multithreading: coarse-grained, fine-grained, and simultaneous. So coarse-grained multithreading is the simplest of all, and the idea is extremely simple. The idea is that if we let's assume, our running example is that we want to run 4 threads on a pipeline. And the pipeline, mind you, is not as simple as the one that we have designed, but it's a complicated pipeline which in principle can also process multiple instructions simultaneously in the same cycle. So this is very simple. What we do is we run thread 1 for n cycles, then we run thread 2 for n cycles, and so on. So we continue in a round robin fashion. So basically what a coarse-grained system would actually do is that it will read instructions from thread, let's say T1, for let's say n cycles, where n can be, let's say n is 10. Subsequently, it will read instructions from thread T2 for the next 10 cycles, then T3, T4, and then again T1, T2, T3, T4, and so on. So one advantage of this scheme is that this scheme is simple to implement, right? And it is true that at any point of time you will have multiple instructions belonging to different threads, but hopefully they will be there in different stages. So managing the pipeline will still be easy. The advantage of this is that just in case thread T1 gets stuck, we can go to another thread, or just in case thread T1 so basically it will basically get stuck if there are some long latency memory operations. So we can quickly shift to other threads, get some work done, and again come back to T1. Our basic insight will hold over here. Then we have, so the implementation is, so let's take a look at the way that this is implemented. So, what are we doing? We are basically running T1 for some time, then we are running T2 for some time. So, we are essentially changing the context, right? So, this is called the context switch. And what does the context contain? Well, the context is essentially the program counter and the registers, right? So, basically, the program counter and the registers for the different threads are different. So when we are running T1, basically T1 will have its own PC registers, temporary values. So when we suddenly load the instructions of T2, we will have to store the state of T1, its last program counter and register, similar to what we had done in the case of interrupts, but of course in a far more efficient manner. And then we'll have to load the last stored state of T2, which is its program counter and registers, right? So this is called the context switch. This operation is called a context switch, changing the context from T1 to T2. And of course it has some overheads. So let us consider a four-way. Four-way means four threads. Coarse grain empty means multi-threaded machine. So a four-way multi-threaded machine. So it will have, so it needs to maintain four program counters, one for each thread. Four register files, one again for each thread. 4 flags registers, one for each thread, and it also needs to have a separate context register which contains the current thread ID. So what do we have? Instead of one PC, we actually have 4 PCs, right? So these are our PCs. 1, 2. Instead of one register file, we'll actually have 4. And so on, right? So then we will also have one more special register called a context register, which will which will store the thread that is currently executing, 1 or 2 or 3 or 4. So if you want to have a very fast context switch, which is called zero overhead context switching, what we can do is that we can design the system with a fair amount of redundancy, as we have just shown, where pretty much the state of each of these threads is maintained in its own PC and register file. So now let's assume that thread 1 is executing. If we want to execute instructions of thread 2, we just change 1 to 2. So immediately the processor will use the program counter and the register file of thread number 2. So this is a fairly fast way of performing a context switch and quickly changing to another thread. And of course, the disadvantage of this scheme is that we need additional space. So as I said, we need to maintain multiple copies, 4 program counters, 4 register files. Depending upon the thread ID, we choose the appropriate program counter or register file. So of course, there is some overhead involved, but this has been shown to improve the throughput of the overall system significantly, especially when we are running programs that have a lot of memory activity, or let's say, consider also such kind of programs which have a lot of IO activity. So there are 4 threads, and one thread sends a message over the network which takes a long time for it to go and a long time for it to get a response. So during the time this thread is actually waiting for a response, one more thread can take over the resources of the pipeline that it was executing in, and it can start executing its own instructions. So in this sense, this is actually a good idea, and that's the reason many server companies, server processor companies, have actually adopted some form of multi-threading. So let's look at the same example that I have been mentioning with some concrete numbers. Assume that thread 1 has an L2 miss. So we need to wait for 200 cycles, which is too much of an overhead. That's the reason we schedule thread 2. Now let us say that thread 2 has an L2 miss. No problem, go to thread 3. So we can always have a very sophisticated algorithm that switches every n cycles, or when there is a long latency event such as an L2 miss, or you're waiting for some IO event and that's taking forever to come. So whenever we have such an event, we can also switch. So it is not necessary that we'll have to wait for n cycles. Before that, if we perceive that we are entering a long period of quiescence, a long idle period, we can switch to the next thread. So the aim is that we want to minimize the number of idle cycles for the entire system and maximize the throughput. So one very good example of the usage of multi-threading would be a web server. So what a web server does is that it has a processor, and then of course it has a memory system and so on. So let's say this is the memory system, and then it has an array of hard disks. Right, hard disks are big blocks of magnetic storage that store the web pages. So there are many concurrent requests for different web pages. For example, if you access CNN.com or you access any other website, there are a lot of websites, and so users request for a lot of websites and images and videos and so on. So in such cases, multi-threading is pretty useful because the processor will quickly process the instructions of the request, then send a message to either the memory system or the hard disk to fetch the file. During that time, the thread is idle. So what will happen is that it instead of it locking up the processor, it will execute the instructions of one more thread. That thread will again do the same, then we'll move to the other thread. And so in this way, we can actually minimize the number of processing elements in our system and take advantage of multi-threading to have a smaller number of processors and still get very good throughput. Now let's take a look at fine-grained multi-threading. So this is almost the same as coarse-grained multi-threading. The only difference is that the switching granularity, which means the time at which we switch, is actually much smaller. It's of the range of 1 to 2 cycles, whereas that was in the range of 10, 20, 30 cycles. So the advantage of fine-grained multithreading is that it can take advantage of very low latency events, such as maybe division or L1 cache misses. So consider the case of division first. So if you go back to when we were discussing computer arithmetic, you would recall that division was a very slow operation. So typically, it would take 10 plus cycles, 10, 15 cycles for a division to actually happen. And even an L1 cache miss might also take 10 or 15 cycles. So these are relatively low latency events as compared to an L2 miss or an IO request. Nevertheless, it is possible that a thread can still get somewhat stuck because it's doing a division operation and it has no other instructions to execute. So during that time, we can bring in other threads, because if the divider is busy, the adder and multiplier are not busy. So they can then process the instructions of other threads. So keeping this in mind, fine-grained multithreading does better in some cases, and we can minimize idle cycles even further. But again, this depends on the particular workload. Of course, there are correctness issues. We can have instructions of two different threads simultaneously in the pipeline. That's a problem. So you need to always keep in mind this point over here. Always keep this in mind, that we never forward or we never interlock for instructions across threads, right? So we never do any forwarding or interlocking activity for any instructions across threads. So it'll never be the case that one instruction will forward its results to another instruction when they're across threads. So this is wrong. And also, we will never stall one instruction because of dependencies across threads. That is also wrong. So all of these things need to be kept in mind while designing the pipeline. So we'll basically have different forwarding units for the different threads. So the forwarding and interlock mechanism will actually become very complicated if we have multiple threads, because we'll have to keep in mind whether these instructions belong to the same thread or not. So yes, there are complexities involved, but it does make a lot of sense to still go ahead with a multi-threaded processor, especially when we are dealing with workloads such as a web server or a file server. Some server which is taking in a lot of requests, doing fairly long latency events like reading a web page or a file from a disk, and then supplying it back to the user. In such cases, multithreading is a fantastic idea. Now let's look at simultaneous multithreading, which is the most flexible of all and also the most efficient. So it is also the most difficult to implement. So most modern processors actually have multiple issue slots, which means that we can issue and we can issue and we can execute multiple instructions in the same cycle, or rather we can issue multiple instructions to the functional units simultaneously. So for example, a 3-issue processor can fetch, decode, execute 3 instructions per cycle. So in our traditional pipeline, every cycle 1 instruction was getting in, and if there are no stalls, 1 instruction was getting out. In an n-issue processor, every cycle n instructions will get in and n instructions will get out, right? So we will see how to do this. Well, we'll actually not see, this is part of an advanced course, but a little bit of how this is done is there in the book, if you would see in the chapter on pipelining. But nevertheless, let's assume that in modern processors this is what happens, that we can send in multiple instructions together and also get multiple instructions out together. Now if a benchmark has low ILP, a program has low instruction level parallelism, which means that it is not possible to actually execute these many instructions in parallel. Why will that be the case? Because we can have dependencies. Let me give an example of some code. Let's assume that I have code of this form. So in this case, there is a read after write dependency like this. There's a read after write dependency over here. So we will not be able to execute these 3 instructions in parallel because there is a dependence between them. So in this case, this particular piece of code has low instruction level parallelism. It has low ILP. So in this case, fine-grained or coarse-grained multithreading will not really help, because we have a lot of dependencies between the instructions. So what do we do for this case? Well, what we can do in this case is something else, which is called simultaneous multithreading. It's also called SMT. So SMT is a short form for simultaneous multithreading. So let us look at the main idea of SMT. So what we do is that if we have an issue processor, we partition the issue slots among threads. So let me go back to the previous example. So here in this thread, we have low ILP. So what's happening is that we have the instructions are totally dependent on each other, right? So if that is the case, then we can always do one thing. We can take thread 1, we can thread 2, and let's assume that its instructions are extremely dependent. The nth instruction is dependent on n minus 1th. So we can't look at executing 2 instructions in parallel. That's all right. So let's assume even the other thread is also that badly behaved. What we can do is that we can actually send instructions of both of these separate threads into the pipeline together. So the pipeline, for example, can then fetch, decode, issue, execute these 2 instructions together, because they can be executed in parallel because they belong to multiple threads. Then we can execute these 2 instructions together. They also can be executed in parallel because they belong to different threads, and their predecessor instructions are done. Similarly, these 2, and so on. So in this case also, we have been able to, in a sense, double the throughput with extremely badly behaved code. And this is one advantage of what an SMT machine can do, which a coarse-grained and fine-grained multithreading machine cannot do. The way we do it is that we partition the issue slots among the threads, and we sort of make it very flexible. So for example, in the same cycle, we can either issue 2 instructions for thread 1, and issue one instruction for thread 2 and issue one instruction for thread 3. So this can be done. So if it's a four-way SMT machine, which means that it can manage four threads simultaneously, and also it's a four-way four-issue SMT, right? So it can manage four threads simultaneously and can issue four instructions simultaneously. We can decide to partition the issue slots among the threads such that the throughput of the overall system is maximized. Of course, we need very smart instruction selection logic, and we have to balance different issues, fairness and throughput. So we don't want to be partial to any thread. We don't want to be biased towards some other thread. So those issues notwithstanding, this is actually a very good idea, and that's the reason most commercial processors, such as starting from Intel Pentium 4 onwards, Intel Xeon, IBM Power 7, all of them implement some flavor of simultaneous multithreading. So let's take a look at this diagram. This diagram actually tells us all. Oops, sorry, this C should have been over here. So this diagram tells us almost everything about what we need to know about multithreading. So let's assume that the rows are actually time. So the rows are cycles. So this is cycle 1, cycle 2, cycle 3, and the time flows downwards. So these rows are cycles, and the columns, and for each case we assume a four-way multi-threaded machine in a four-way four-issue multi-threaded machine, right? So we can handle four-way, means we can handle four threads at the same time. Simultaneously we can handle four threads, so that makes it four-way. In addition, each of these are four issue machines. So four issue means we can issue four instructions together, right? Into the pipeline we can send four instructions together. That's the reason each of these diagrams has four columns, where the columns are basically the issue slots. Alright, so let all the instructions belonging to thread 1 be green, all the instructions belonging to thread 2 be this color pinkish, all the instructions belonging to thread 3 be blue, and all the instructions belonging to thread 4 be this color, which looks like somewhere in purple and maroon to me. Let's, for the time being, let me call it purple. So what a coarse-grained multithreading system would actually do is that it would execute instructions belonging to the same thread for n cycles. So let's assume, just to keep the diagram simple, n is 2. So you would see that first it is executing instructions of thread 1, then it executes instructions of thread 2, then thread 3 and thread 4. So all of these white slots are unused slots, right? And why do we have unused slots? We have unused slots, unused issue slots, because it was not possible to find instructions belonging to thread 1 that could have been executed in these slots. Why were we not able to find instructions? Well, we were not able to find instructions because their operands were not ready, right? So their predecessor instructions that are supposed to generate values for them, those instructions had not executed. So we simply did not find enough instructions of one thread that we could execute in parallel. Consequently, we wasted issue slots, and that's the reason we have many of these white squares. In comparison, we can do fine-grained multithreading. So here, instead of every 2 cycles, we switch every 1 cycle between the threads. So we first execute thread 1, then thread 2, then thread 3, then thread 4. Again we come back to thread 1, thread 2, thread 3 and thread 4. So as you can see, this situation does not improve significantly. In fact, these two diagrams actually have the same number of white squares, which basically tells us that we have not been able to do very well in terms of reducing the amount of idle work. And of course, I have not factored in the effect of short latency or long latency operations. Otherwise, there would have been some amount of difference, because it's possible. Consider thread 1, right? So in thread 1, initially we have two instructions ready. So that's the reason in cycle 1, both coarse-grained and fine-grained multithreading systems will execute the same number of instructions. But it's possible that here we find three instructions to be ready, but by this time maybe one more instruction is ready because its predecessor is done. So in a sense, fine grain has a potential to be better, even though I have not shown it in the diagram. But what is genuinely really good is simultaneous multithreading, because what we do is that in every cycle we partition the issue slots among the threads. For example, in the first cycle we have instructions which belong to both thread 1 and thread 2. Similarly, in the second cycle we have instructions belonging to different threads. Third cycle we decide we'll only have instructions of thread 4. So with a very very smart scheduling scheme, what we have effectively done is that we have reduced the number of white squares to only one, which means the amount of idling is very little. That's the reason we also get done sooner with the instructions of all the 4 threads, and our throughput is very high. So this diagram should in a sense show the superiority of simultaneous multithreading SMT over the other approaches, mainly because in the same cycle we are able to bring in instructions from different threads and smartly decide the allocations and execute them. As a result, you can see that we are done much sooner, and we have a great performance advantage. So we will in a sense end here, but the important takeaway point is that most modern processors support simultaneous multithreading, and it's a great idea to actually have it and to use it. And sometimes operating systems show a different. For example, in this case, if we have 4-way multithreading, some operating systems, depending upon how they are configured, can actually show that we have 4 virtual CPUs, right, on the same physical CPU. So, operating systems can expose multithreading in different ways to the normal user. And the most common way is that every single, in a 4-way multithreading system, 4 virtual CPUs are exposed to the programmer, and then the programmer can write regular code the way we have been writing in this chapter, right? With OpenMP, with MPI, or without any parallel directives, the way we wrote code for a sequential and weakly consistent system. So in any way, the programmer can write code and execute on this system, and each thread in this multi-threaded machine is pretty much looks like a CPU to the programmer and the compiler. Alright, now that we are done with multi-threading, let's take a look at another paradigm, which is called vector processors. So vector processors is not a MIMD machine. So multi-threading was nevertheless still MIMD. So this is a SIMD paradigm, single instruction, multiple data. And for some programs, vector processors are absolutely fantastic. So they used to be the mainstay of supercomputers for a long time now. Even now also vector processors are very useful. So we will discuss vector processors and also vector instructions, vector extensions to normal instructions. And we'll also show a real life example and show how useful vector processing can actually be. Let us now define a vector instruction. So a vector instruction, instead of operating on single pieces of data like regular instructions, it operates on an entire array at a single point of time. So instead of one data item, it operates on arrays at a time. For example, we can have vector instructions to add or multiply 2 arrays of data element wise. For example, if one array is 1, 2, 3, 4, and the other array contains 4 elements 5, 6, 7, 8, then a vector instruction can process both the arrays. A single instruction can add the two arrays, so it will produce 6, 8, 10, and 12. So previously what we would have done is that maybe we would have written a for loop, or we would have had multiple instructions to do adds. At least we would have required 4 add instructions. But in this case, a single instruction will take care of such kind of operations. And such kind of operations are actually very useful. So they can be used to perform all kinds of array, matrix, and linear algebra operations, and everything to do with matrices, which is pretty much the bedrock of many scientific applications, graphics applications, and data analytics applications. So all of these kinds of applications use linear algebra as their core, and that is basically vector and matrix operations. So vector and matrix operations will significantly gain uh, by having vector instructions. So let's look at the background. Vector processors were traditionally used in supercomputers. So these vector instructions and processors that support vector instructions are vector processors. So they were not used in regular computers, but they were used in supercomputers meant for very sophisticated applications. So you can read about the processor called Cray-1. So Cray was an early supercomputer which had vector processing. But subsequently, vector processing is not just limited to Cray. It has come into other processors as well, and it has vector instructions have found their way into mainstream processors. So the instructions, so mainstream processors such as x86 processors also support vector instructions. So they have extensions to their ISA to support vector instructions. So in that sense, vector processing has come into regular mainstream processors. So for example, Intel processors support the MMX, SSE 1, 2, 3, 4, and AVX instruction sets over and above the baseline x86, which all of us have studied, such that it is now possible that I can take a regular Intel processor and then I can run vector instructions on top of it. So I can run, regular x86 instructions and also vector instructions like, SSE 2 instructions on it. Why would I use the vector instructions? I would use them if I foresee a certain amount of speed up. On similar lines, AMD has created its vector instructions. So AMD has a 3D Now vector instruction set, and the 3D Now instruction set is somewhat conceptually similar to MMX, SSE 1, 2, 3, 4, and AVX. So that also extends AMD's x86 support with new instructions. So let us look at the software interface of a vector instruction. So we need to define a vector register. A vector register, as opposed to a scalar register, can actually contain multiple values, an array of values. For example, 128-bit registers in the MMX instruction set. For example, we have 128-bit registers in MMX instruction set, which is a vector extension to x86, right? So it has 16 of such 128-bit registers. They are called XMM0 to XMM15, XMM0, 1, 2, 3, 4 till 15. And each of these registers, which is in a 128-bit, can hold 4 floating point values. Right, so one floating point value, if you assume it is 32 bits, so 4 of these can be held within one of these registers. Or additionally, we can hold 8 2-byte short integers, where one integer is 16 bits. So 8 of these can be held within each of these vector registers. So one register is basically an array. So in one form of it, it can hold 4 floating point values. In another form of it, it can hold 8 short integers, right? 4, 8, a total of 8 short integers. So these are the two forms of the vector of the XMM vector registers. So the addition of vector registers is basically equivalent to pairwise addition of each of the individual elements. If let's say there are two vector registers, for each we are assuming that they have 4 values. Then we'll just add the values pairwise. So the final output will also be a vector, which will be stored in one more vector register. And each of the values, so this value is a sum of this and this. So note that if I add these two values, no carry is transferred here. This does not happen, right? Because for all practical considerations, these are different values, right? So there is absolutely no movement of any carry across, this part of the vector register and this part, right? They are separate. Finally, the result, which is this, is saved in a vector register with the same size, which is 128 bits in this case. So this is one more visual look at vector addition. So let's assume that we have vector registers. So let us add 8 128-bit registers, vector registers in SimpleRisc. Let the registers be VR0 to VR7. So this vector register 0, vector register 1, 2 and 7. So what we'll basically have is a conceptual view when we are adding two vector registers VR1 and VR2. What we basically add is if we assume they are containing multiple fields, floating points or shorts, doesn't matter. The addition is always pairwise. So if this is 3 and 2, this will be 5. If this is 10 and 11, this will be 21. So now let's take a look at the load and store operations of vector registers. This is difficult in the sense that there are two ways of doing it and both the ways are fairly different. So there are two options. One is that we assume that the data elements that we want to load are stored in contiguous locations. So this will make our life somewhat easy. As compared to other approaches, this is the easier one. So let us define the v.ld instruction. v.ld is vector load instruction that uses this assumption. So let the semantics of this be v.ld vector load vr1 and then a memory address. So here what we do is that we go to the memory address and we load the subsequent 16 bytes. So one starts at R1 plus 12. One address, another address starts at R1 plus 16, one at R1 plus 20 and one at R1 plus 24. At each of these addresses we load 4 bytes. So we are assuming that the total size of the vector register is 16 bytes or alternatively 128 bits. And since we are making an assumption which is a strong assumption that we want to load 16 consecutive bytes, of course in groups of 4, from one area, from one memory area. So basically we are loading these 4 integers or 4 floating point values into a vector register VR1 in this case, right? This is the semantics. So this is simple. The other option is slightly more difficult but not that difficult. We assume here that the elements are not saved in contiguous locations. They are stored in any random location. So such kind of an access pattern is known as a scatter-gather access pattern. The reason is that the data is scattered in memory. So the load operation needs to gather all the data and save it in a vector register. So let us define a scatter-gather version of the load instruction. Instead of v.ld as v.sg, s for scatter, g for gather, v.sg.load. So this will use another vector register that contains the addresses of each of the elements. So the format of this particular instruction will be something like this: v.sg.ld, vr1 and vr2. So vr1 is the vector register that needs to be loaded, and vr2 is the vector register that contains the addresses. So we assume a 32-bit memory system. Then the 4 addresses are in vr2 0, which is the first 4 bytes, vr2 1, the second 4 bytes, VR2 2 and VR2 3. So each of these is an address. So we need to access this address and then get the value that is stored in there. So all of the values come and then they populate the vector register VR1. So in this case, the hardware needs to do more work. So let me maybe write it down. So one clear negative aspect is that the hardware needs to do more work. So it basically, we need to send 4 different memory requests and they need to go to 4 separate addresses, fetch the data. Whereas in the previous case, there would have been a strong possibility that we would actually find all the 4 data items within the same cache line, within the same cache block. So that would make it much easier and a single access would suffice. But in this case, much more work is involved. Nevertheless, this instruction also has some advantages, particularly if our program exhibits such kind of a scatter gather kind of behavior. We can similarly define 2 vector store operations. So one is a normal store, other is a scatter gather store. So the first argument of the store operation is essentially the data that needs to be stored, and the second argument are the addresses. So in this case, this is scatter gather store. So basically the elements of VR2, namely VR2 0, VR2 1, VR2 2 and VR2 3 contain the addresses. So at these addresses we write the values in the vector register VR1, which are its elements 0, 1, 2 and 3. We have another flavor of the same instruction where again VR1 is a vector register that contains the data. But instead of a scatter gather kind of operation, we give it a memory address and we assume for the subsequent 16 bytes, the data from VR1 is taken and written. So in this case, VR10 is, so we take the contents of R1 add 12, that's where VR10 goes. Similarly, VR11's data, 4 bytes, goes to R1 plus 16, 17, 18 and 19. Similarly for VR2 and VR12 and VR13. So more about vector operations. So we can define more custom operations on vector registers. For example, we can define a vector add instruction to add 2 vector registers. We can define a vector multiply instruction to multiply 2 vector registers. But mind you, these are pairwise. So both of these are pairwise addition and multiplication, which means that we consider each element of the vector register and essentially add all the elements separately. We can also have other operations which are there in vector instruction sets typically, that we have a vector operand and a scalar operand and we multiply the vector by a scalar. For example, if we have the vector 1, 2, 3, we multiply it by 2. So the final result becomes 2, 4 and 6. So all of this is possible. So modern instruction sets have many vector instructions depending upon what is required, depending upon the programmer's requirement. So let us now consider an example where we add 2 arrays of floating point numbers using Intel's SSE instruction set. So SSE is an extension of the x86 instruction set, so it has vector capabilities. So we have one floating point array A, one B and one C. The final aim is to essentially create a vector C, which is vector A plus vector B, where the elements are added pairwise and we have n elements. So we are assuming that our registers are 128 bits wide. So 128 bits is 16 bytes. So it's essentially a sequence of 4 bytes where one 4-byte field is a 32-bit field. So this contains one floating point integer. So pretty much one vector register, which is all of this, one vector register contains 4 floating point values. So since we can process 4 values together, the number of iterations that are required is n divided by 4. So that is the number of iterations. So this process of reducing the number of iterations is called strip mining. So then we simply run a for loop from I equal to 0 to I 0 to num iterations minus 1. So we need to do several things. The first thing is that, so let's consider the first iteration, right? So we have the pointers A, B, and C, which look at different memory regions. And so let us take the first 4 floating point numbers in A, the first 4 floating point numbers in B. Let's add them pairwise, and then let's save the first 16 bytes, save them to the first 16 bytes in C. So the process of loading the values is achieved by calling a built-in function the GCC compiler provides, called _mm_load_ps. So this basically encapsulates an assembly instruction, and the assembly instruction loads 4 floating point numbers from the current pointer value A and saves it in the vector register val1. Similarly, the assembly instruction loads 4 floating point numbers from the pointer B and saves it in the vector register val2. So the vector registers val1 and val2 contain 4 floating point numbers each. So then we perform the vector addition. So again there is a built-in function. So each of these built-in functions actually encapsulate real assembly instructions. So just so that the programmer does not have to use real assembly, these functions are provided. Also later on, if the programmer is using these functions and the instruction set changes, then the programmer's code at least will not need to take care of that. So we have one more function _mm _add_px. mm basically stands for mmx. And in this case, we are adding the vector registers val1 and val2 pairwise. And the result is stored in another vector register res. Finally, we need to store the result in C, which is the first 16 bytes of C. So we take this vector register res and save it in C. The first 16 bytes are saved in C. _mm_store_ps is the function. So this is a normal vector store operation. It's not a scatter gather store operation per se. So this helps us store or write into the first 16 bytes of C. So now once we have done that, we have at least processed the first 4 entries in each of the arrays A, B, and C. So then we can simply update the pointers for A to now point here. So let this be the new value of A. Sorry. Let this be the new value of A. Let this be the new value of B. Let this be the new value of C. So we can do this. We can continue the same process. So to do that, we need to increment the pointers in C. So we do A plus equal to 4. So since we already know that A is an array of floating point numbers, and each number is 4 bytes. So what we are doing is, if let's say capital A is the address of A, we are actually doing A plus equal to 16, right? So that's the way C works. That C essentially multiplies 4 with the size of the data type contained within A. And same is the idea. C means C language, not the C array. Similarly, for pointers B and C, we essentially add 16, 4 times 4, because 4 bytes is the size of a floating point number. So we add 16 to the pointers B and C such that they again come here. Again, we consider the first 4 bytes from here. We add them pairwise and store them in C. And again, we update the values of A, B, and C. So we continue this till these entire arrays are scanned, and we add them pairwise, and the results are written into C. So you're welcome to take this program and run it. It should run on almost all systems, on almost all Linux and Unix like systems which run on x86 processors. So what you will see is that this piece of code that uses vector instructions is roughly 2 times faster. So the speed difference is quite a bit. It's around 2x or 2 times faster, and it can actually be more. So the modern AVX instruction set also has 512-bit registers. So which means that we have really wide registers which can be used by almost all programs that have something to do with linear algebra or arrays, matrices. So, but in this code, if you just run it, you will see a 2x speed up, which is significant. In a 2x speed up, getting it with hardware improvements will easily take us, 5 or 6 Moore's law cycles, or something like 15 years. But this you can easily get just by changing the code from a normal for loop based addition to an addition that uses these SSE instructions. Now let's consider if statements in the world of vector processes. So suppose we want to run the following code snippet on each element of a vector register, which is if x is less than 10, if where x is the value, mind you, it's not a vector, it's a single value. So if x is less than 10, we'll have x equals x plus 10. So for example, if we have a vector register which is of the form 1, 11, 2 and 16, so the final result will be, since 1 is less than 10, 11, 11 is not affected. Then since 2 is less than 10, we'll have 12 over here and 16. So let's say this is what we want to achieve. So in this case, let the input vector register be VR1. So let's first do a vector comparison. So let us compare the vector register with a scalar, which in this case is 10. So what we will actually do is we'll compare each element in the vector register with 10. So we'll compare 1 with 10, 11 with 10, 2 with 10, 16 with 10. Subsequently, what we will do, so let's consider the elements. Each of these we are comparing with 10. So we'll save the results of the comparison in a vector flags register, right? A flags register which contains multiple values. So in this case, 1 is less than 10, so this comparison is true. 11 is not less than 10. 2 is less than 10, so the comparison again true. And 16 is not less than 10. The comparison is false. So we'll essentially, instead of producing a single flags register, we will produce a vector flags register, which will hold the result of the comparison. So in this case, so we can have what we had in our pipeline, which basically means that we can have, a flags.e flag and a flags.e field and a flags.gt field. So it depends, we can, there are many ways of creating a flags register. So here I'm assuming that the flags register is just containing a set of Boolean variables of whether the comparison was successful or not. But there are many ways. But in general, if you are comparing VR1 and 10, it is actually better to have two fields in the flags register, E and GT, right? So let's do it anyway. But once we have a flags register which is telling us the results of the last comparison, so essentially in our case we can, let me just go back. So the flags register, it doesn't matter what fields it has, it is essentially recording the case that in the first case we had a less than equal to. In the second case we did not have a less than equal to. Sorry, not less than equal to, less than. In the third case we had a less than, and in the fourth case we did not have a less than. So irrespective of however we implement it, this is the information that we need to capture. Now let's say a condition is true, then the predicated instruction needs to get evaluated, otherwise it is replaced with a no op. So let's see what this means, because this is fairly involved and will require some discussion. So what we have seen on the previous slide, what we have seen on the previous slide is that we compare each element of VR1 with 10, and then we produce a vector form of the flags register which has the results of the comparison. So we compare 10 with each element. So we'll have 4 results. But now that we have these results, what do we do now? So if we have these results, so one thing is that we cannot run a small mini loop inside a vector and do a separate test for each and every entry. So in a certain sense, this violates the core principle of vector processors, which basically tell us that we should not do something separately for each entry. We should do the same thing for every entry. So that's the reason for every entry we compare and we have the results of the comparison, which is less than, not less than, and not less than. I hope, yeah, that's right. So now what do we do with it? What we want to do is that we want to set VR1 as VR1 plus 10, but not for all the elements. Only for those elements that are less than 10. So go back to the code. Only for those elements that are less than 10, we want to add 10 to it. Not for all the other elements. So there has to be some way of doing this, right? So what we can do is we can take some amount of inspiration from the ARM ISA, which had similar predicated instructions. So let's first see what happens in ARM. So we had an instruction in ARM called add EQ or add equal. So the add EQ instruction took R2 and R3. It added R2 and R3, the contents of R2 and R3, it added them. And it saved the result in R1, right? So in R1, the result of the addition of R2 and R3 was stored. But there was an additional caveat, which was this EQ field. This said that if the previous comparison resulted in an equality, then only we do this addition. Otherwise, we don't do anything at all. So let's assume that the previous comparison resulted in things being equal. Then we will set R1 as R2 plus R3. However, the previous comparison led to an inequality. Then this instruction becomes a no-op, which means that it doesn't do anything, right? So that was our basic philosophy of the add EQ instruction. So let me repeat, if the previous comparison, right, before add EQ, if that had resulted in an equality, then only we do this addition, otherwise we don't do anything. So let us now define a vector form of this predicated instruction to do what we have set out to do. So in this case, let's create an instruction of the form v.p.add, where p between this condition is the predicate. For example, we can say v.lt.add. This basically means that for all of those elements inside the vector register where the previous comparison led to a less than, we only perform the addition for them. So basically it's a regular add instruction for the elements in which the given predicate, which is less than, is true. For the rest of the elements, the instruction becomes a no-op. So let's look at some common examples of predicates. LT is less than, GT is greater than, and EQ is equality. So in our case, if you want to do this, then the implementation of our function actually becomes very easy. So we define, so if let's say this is what we want to do, that given a vector, for every element, right? So mind you, this is, you want to implement this function for every element of the vector. So if x is less than 10, we want to set x is equal to x plus 10. So in this case, what we do is that the first we compare VR1 with 10. So let's assume, let's look at a running example once again. It is 111, 216. So let us consider the vector v, which is 1, 11, 2, and 16. Let us compare each of these elements with 10. So in the first case, if we just consider from the point of view of the predicate less than, of course the results are saved in a flags register. So I'm not, I'm not showing that part. But of course this part is implicit, that the results are stored in the flags register. But if we just consider the predicate less than, then 1 is less than true. 1 is less than 10. So in a sense it's true. 11 is not less than 10. So this predicate is false. Is 2 less than 10? Well, yes, so this predicate is true. Is 16 less than 10? Well, the answer is no, so this predicate is false. So basically at this point, what we do is that we add we add 10 to each and every element of VR1. I'm sorry, this should be VR1. So we add 10 to each and every element of VR1, and we save the result in VR1. But of course, this is not a normal add instruction. It's a predicated add instruction with a predicate LT, which means that when we'll actually perform the addition, we'll consider the elements of VR1, and so the elements of VR1 will be 1, 11, 12, and 16. So let me write that once again. I will add this to 10. So the result, which is also VR1, will depend upon the values of the computed predicate, which in the first case is true. So we'll go ahead with the addition. In the second case is false, so we will not do the addition. So the result will still be 11 because 11 is contained here. Oops, sorry, this should not be 12, it should be a 2. So in the third case, yes, the predicate is true because 2 is less than 10. So in this case, we will also add 2 plus 10 and make it 12. And in the fourth case, the predicate is false, so we will not do anything. So the final result will be 11, 11, 12, and 16. So this is how we can actually perform a vector comparison and then a predicated vector add. So what is the advantage of doing a vector addition in this way? Well, the advantage is that we are completely avoiding all kinds of for and while loops, right? So we are not iterating through each and every element of the vector. Rather, we are treating the vector as one atomic whole. So basically, the entire vector is being treated in an atomic fashion. So we treat the entire vector as one. We can do a comparison. We can also define a vector compare where we compare the vector with one more vector. But the important fact is that we have a vector flags register. Subsequently, when we define any instruction of the form v dot the name of the predicate, less than, greater than, less than, equal to, doesn't matter, anything, and the add. So in this case, add or sub or mul, doesn't matter. The important fact of the matter is that any such instruction first takes a look at what are the computed predicates, right? For less than, we basically take a look at the flags register and find out which of the elements evaluated to a less than. For greater than, we find which of the elements evaluated to a greater than. And based on that, for all the elements for which we evaluated true, we actually perform the operation, and for the rest, we don't. So in this manner, it keeps the hardware very simple and straightforward. And so it does not complicate the hardware at all. Basically, you can consider the flags as kind of a mask, where in some cases we perform the operation, for some elements we don't do anything at all. So number one, it keeps the hardware simple, right? Number two, it eliminates. So this also eliminates branches, right? All the branches that are there in an if statement, in a for loop, and in a while loop. All of these branches are eliminated. The hardware remains simple. Of course, we do a little bit of extra work in the sense we compute predicates we take into account these false predicates. However, the simplicity of the hardware and the elimination of a branches is a massive plus. So this can also be done for small vectors, for very, very large vectors as well. But the mechanism of having predicated instructions per se is very powerful. So now let's take a look at the overall design of a vector processor. So some of the salient points are like this, that we have a vector register file. So most of the common general purpose processors also qualify as vector processors because they have vector instructions. They also have scalar and vector functional units. And unless we are converting a vector to a scalar or vice versa, we in general do not forward values between vector and scalar instructions. So this is one thing that's kept in mind, that in the pipeline, forwarding of values between the vector path and the scalar path is not done, because typically, this need will not arise. And also the memory unit has to be more sophisticated, right? The memory unit and ALU to compute the predicated instructions, they need to be more sophisticated. In particular, the memory unit needs support for regular vector operations, regular operations, vector operations, and possibly scatter gather vector operations if they are supported. Now let's take a quick detour and look at graphics processors. Graphics processors are, well, they have some multi-threaded features, some vector features, it's a mix. So before I explain this diagram, let me at least give you a very, very brief and short overview of graphics processors. So graphics processors are, this is how they fit in, that if we have the standard processor, the CPU, so typically, in modern systems where you have games and movies and all of these things, a lot of the work of actually, processing the videos and generating the scenes has to be outsourced to a dedicated processor called a graphics processor, right? So this can either be inside the chip of the processor or can be outside, it doesn't matter. It's a separate piece of hardware, right? And the major vendors of graphics processor, at least as of 2015, 16, 17, are essentially NVIDIA, Intel. Intel has built its own graphics processors, and ATI, AMD. So ATI was a company, AMD acquired it. So, graphics processor original aim was just to process videos and render scenes and games and so on. But later on, computer architects realized that graphics processors have a massive numerical capability. So they can be used for doing regular linear algebra and scientific computations also. And in fact, they can actually do it very, very well. So that's how, now instead of GPUs or called graphics processing units, we have GPUs. So GPUs, where this stands for a general purpose graphics processing unit, right? So G is for general, P is for purpose, and so we thus have GP is for general purpose and GPU is graphics processing unit. So GPU. So that is a broad idea, that in a GPU you have a mix of everything. So you have MPMD style, which means you can run multiple jobs, and then multiple jobs will have different instructions. So that can happen. We also have SIMD kind of programming where you'll have multiple threads with exactly the same instructions. And you will also have fine-grained multi-threading. So it's a mix of all. So we can't. So actually, the term that NVIDIA uses is SIMT, is same instruction, multiple threads. But it does not matter what exactly is the classification, as long as we broadly realize that they are different from traditional single-core processors. Because graphics processors will typically have many small cores. So they'll typically have many cores. Maybe 128 cores or 256 cores, where each core is very small. So let's take a look at briefly about the background. So modern computer systems have a lot of graphics intensive tasks. So these are computer games, computer aided design, particularly in engineering, architecture, high definition videos, and then desktop effects. You would have seen on especially Mac processors that if you click a button, then icons suddenly enlarge. And so there are a lot of very glitzy features on a desktop itself, and all of these things happen with the help of graphics processors. Because if you, let's say, disable your graphics processor, you'll certainly find that the desktop experience is very jittery and slow and sort of doesn't look good. So all aesthetic software features in games, videos, everything is all the the has been contributed to us by graphics processors. So since graphics plays a very important role, it was observed that the amount of processing required is very high. And furthermore, we cannot tie up the processor's resources in doing graphics. Because number one, a general purpose processor is not tailored towards doing graphics. That's point number one. Otherwise, you will require a huge amount of processing power. And the second is that the processor will get completely tied up. So it can't do other things. That's the reason you use a dedicated graphics processor. So, what does a quintessential graphics processor do? So, it processes a set of objects in a game to essentially create a sequence of scenes. So, the important thing is how exactly does a game work? So, we would have seen these in a fantastic games where there are features. So, there is one mountain like this, one more mountain like this, and one character. Sorry, I'm a bad drawing person. So, one character keeps running this way, jumps from one mountain to the other, and then some other characters come and they shoot bullets. So you can have a lot of action in a game. So the way that the game developers write the game is that they sort of create these high level rules with how these individual characters interact between themselves and the environment. Subsequently, after layers of software, still pretty high level instructions go to the graphics processor. So what the processor would do is that it processes a set of objects in a game and it creates a sequence of scenes. Also, it is able to apply shadow effects, right? Shadows of characters, illumination effects. And what it does is that a complicated 3D scene, it sort of converts it to a 2D image, because ultimately a monitor will show a 2D image, right? So a monitor, let's say it's a 1024 by 768 monitor, so it can only show that many pixels. So a complicated 3D scene with a lot of objects and characters is finally converted to a 2D image. And the 2D image, we can further add in a color information, the colors of faces, and you can add textures, right? So for example, wood has a different texture, metal has a different texture. So all of this can be done. So we can create a really, really, visually vibrant scene. And this will essentially be passed on to the monitor, which will show the scene. Graphics processors also, do a little bit of physics. In a sense, you would have seen some of these movies like the Pirates of the Caribbean and, many, many more Hollywood and Bollywood movies, where there are lots and lots of effects. So a lot of these effects are actually computer generated, in the sense that, it's not real water, or it's not even the case that the film crew has actually gone to the middle of an ocean. Instead, what they have done is that they have basically used a computer to create all of those scenes, right? Create all of those water-based or land-based scenes, and graphics processors have a lot of role to play in it. In addition, they do traditional stuff also, like play videos. So they have an MPEG-4 encoder and decoder to do the job. So a traditional pipeline of a graphics processor, this is the way that it looks. So we have a set of shapes, objects, rules, and effects. So shapes can be the characters, objects can be, shapes can be things in the background, objects can be the characters, rules can be the way that they actually interact, and then we can have, effects are the rules of interaction. So the first step is actually vertex processing. So in vertex processing, what happens is that we perform basic operations on shapes, on all the shapes, and represent the entire scene essentially via a set of triangles. So that is true in almost all graphics kind of operations, where we take a rather complicated scene and we break it into triangles. Subsequently, what we do is that these set of triangles, which incorporate pretty much all the rules and all the effects, are sent to a rasterization engine. So this engine will convert all the fragments that we have to basically pixels. In addition, both of this information of fragments, as well as so basically we'll take in triangles and make small fragments of pixels, right? And these fragments will go to a fragment processing engine, which will add additional color and texture information. For example, we will have a small rectangular fragment, and this can be a piece of wood. So the fragment processing system will actually, make it look like it's a piece of wood. Finally, after doing that, we'll create a set of pixels, which is just a 2D array of pixels. And this will go to the frame buffer processing unit, which will finally process this and send it to the monitor, which will finally show the image. So the frame buffer processing also what it does is that it does the final it does the final round of processing, which means if you just in case we have a 3D scene with multiple layers, where each layer has gone through each of these steps, so then it adds additional depth information and converts the 3D scene to a 2D scene. I mean, it's not a 2D scene, but it's essentially a 2D array, right? And the scene can be 3D, but if you add a little bit of depth information, then it'll make we'll get an idea that actually we are watching a 3D movie or a 3D game, but in reality, what our monitor will actually show us is a 2D matrix of pixels. So this will be done by the frame buffer processing unit. So this is the traditional graphics pipeline. And almost all graphics processors have a similar way of processing images and videos and everything. So that part is fine. But after this, researchers realized that with so much of numerical capability, we can use the graphics processor to do other smarter things as well, such as general purpose equation solving and scientific and programming scientific applications. This lecture ends over here. So in the subsequent lecture, we'll start from this slide. So we will not look at the graphics part of the graphics processor. Rather, we'll treat the graphics processor itself as a computational engine, and we'll see that how it can be used to actually do complicated computational tasks, general purpose tasks. So we'll start from here.